I wanted to go through an interesting circuit example that uses basically linear resistive circuits, but also has some very kind of interesting typical elements, including it also has a voltage controlled current source. And again, this is going to be a very typical structure. For those of you who are looking at this circuit and have done some circuits before, one of the things you're going to look at this and go, wait, this looks like a BJT or a MOSFET amplifier. And the answer is with a bunch of resistors. And the answer is yes, it is. That's exactly where it came from. And so this illustrates a number of those kinds of circuit techniques that you might have to think about. Okay, so when you look at a circuit like this, sometimes the first reaction people will go is like, where do I begin? How do I begin to start with this? And often kind of thinking through these and knowing where to begin is important, and having practice of looking at this is important. So what can I see when I look at the circuit? Well, one of the first things I notice if I look sort of back from this position A, that I notice I have this interesting sort of input voltage, right? And this is really a voltage to ground. So you can imagine it being drawn as a voltage source, much like I drew the second one, which is 5 volts. And you think, okay, so either way that would have worked. Often we'll think about inputs like this. And then I have something sitting at 5 volts here, so 2 voltage sources and 3 resistors. Now I know I should be able to combine all that into a single voltage source and a single resistor, right? This is sort of the theory around one-port networks, and we're talking about Thevenin and Norton equivalence and so forth. So you begin to say, well, how would I solve it? Well, one way to think about this would be to say, well, imagine what is the voltage here at A, and I'll call it VA. And I can imagine what is the component of that due to just Vn alone and just 5 volts alone. Well, why can I do that? Well, that's called superposition, right? I can turn them on separately. I can turn them in any sort of combination as long as I eventually complete it. Well, in this case, I can start off by talking about, well, VA due to the 5 volt term is related to a whole parallel combination of all of these resistors, basically all of them being set to ground other than the one I am connecting to. Similar sort of thing I can say is, what's the voltage for VA just due to VN? And I go, oh, I can think about that one as well. And I get a similar sort of conversation there. Well, if I look at that and I say, well, what is that? I could imagine building what is my two-port network, one of which is saying, what is my equivalent resistance? Well, that's really easy because that's all 3 resistors in parallel. Kind of why I started drawing it this way in the first place. And we know that's about 4.5 k ohm if you're actually substituting in the values. I kind of wanted to do both so you could see both in this conversation. If you're asking what is that equivalent voltage, which is that equivalent voltage I'd be seeing at A due to both the 5 volts and the Vn, well, I just have to add these 2 responses. And if I do that, this is the expression I get, and these would be the numbers I would see as a result. A lot of times we would want to know that because we're often setting up all these resistors and voltages to kind of bias, say, a voltage-controlled current source, which you might also think of as a transistor, because transistors do that pretty well. There's other ways to do it, but they do that very well. And how you kind of set that in the right place. Okay. So once I have that, what else do I know? Well, I know that RB is infinite, so I'm just kind of, basically it's an open circuit, so we'll just kind of work with that. Sometimes you could actually go back and rethink through this whole derivation, assuming that it wasn't, and that would actually be a really good sort of learning exercise. But assuming that's the case, well, now I could write an equation for KCL at V2, which then gives me this expression for GMV1 here, and then I know that V2 is related to this voltage and a drop of V1. So it allows me to come up and solve this, which then actually gives me a nice analytic sort of gain term between the two. Those of you familiar with more advanced circuits, this sort of GM times RE is exactly what you'd expect for sort of a source degeneration or emitter degeneration resistor to kind of help you set a transconductance term. And then the last thing you see is there's a KCL at V out, which is just basically take V out here. And as a result of it, I find that V out is going to be equal to the negative of GM RC V1. I basically did it in magnitude here. And what I would find is that, what I'm going to get here is a gain of about 200. And so then as a result, in magnitude, my V out is going to basically be related to about 9.52 of VA. Again, this is in magnitude, the signs are actually negative. And I could actually look at this all the way from V in, which is kind of interesting because it basically means from input to output in this particular structure is just short of just slightly under 1. But this kind of gives you an idea how you would work through some sort of a circuit and sort of see these sort of things. And there's nothing terribly scary. In fact, in a typical circuit where you see voltage controlled current sources, there's usually actually explicit reason that actually makes the overall circuit work a little bit easier. So don't be afraid when you see them, because a well-written problem, typically these things are not meant to be scary.